Good day to everyone, and welcome to the first online oral session of Science and Technology 2025. My name is Luis Gaya, and I am one of the scientific program leads of the Science and Technology 2025. Today, I have the pleasure to work with my colleague, Ronan Lebrun. He is the person who will be writing the report of the conference after the conference. So we have today 7 outstanding oral contributions for you that they fall under all the topics of the conference. We will be listening about machine learning, about atmospheric transport modeling, infrasound perturbations, and outreach activities. The authors could not join us in Vienna, and therefore they send us a pre-recorded talk. We will be playing each one of these talks, and after each one of the talks, we will open the floor for questions. Remember, you can submit your questions via the virtual platform or via the mobile app in your phone. At the end of the session, if there is time, we'll open again the floor for questions about each and any of the presentations. And with nothing else to add, let's start with the first presentation. The title of the presentation is Model of Atmospheric Gravity Wave Perturbations and Their Effect on Localization of Infrasound Field and Its Sources by Igor Chunchuzov from the Institute of Atmospheric Physics of the Russian Academy of Sciences. Let's listen to this pre-recorded talk.
Today I would like to present some new results on modeling Today I would like to present some new results on modeling of the influence of atmospheric gravity wave perturbations on the localization of infrasound field and its sources. At present time, infrasound community has realized that wind velocity and temperature fluctuations caused by atmospheric gravity waves play an important role in infrasound propagation in real atmosphere. This perturbation causes fluctuations in the travel time, amplitude and direction of propagation of infrasound signals. Also, they lead to the error in determining the location and power of various infrasound sources such as explosions, volcanoes, meteoroids, thunderstorms, tornadoes and others. Correctly accounting for the influence of these perturbations on the parameters of infrasound signals is crucial for the solving of the problem of infrasound monitoring of natural and anthropogenic sources. There are different models of atmospheric gravity wave perturbations. Most of them constrained so that the vertical wave number spectra of these perturbations follow the universal power law decay with decreasing vertical scales of the perturbations, and the spectrum takes a -3 slope when the vertical scales decrease in the stratosphere, for example, between 2 kilometers to 100 meters. However, these models do not take into account that horizontal wave number spectrum also takes some universal form with the -3 power law decay in some range of horizontal scales. The existence of such a steep horizontal spectrum was confirmed in the aircraft measurements of the wind velocity and temperature fluctuations in the stably stratified upper atmosphere over Arctic region of Russia and over Greenland. These results of aircraft measurements are presented in the papers shown here. Here are shown the vertical effective sound speed profiles taken from the nonlinear model of formation of gravity wave spectrum. These profiles are taken with horizontal step of 28 kilometers. The main mechanism of formation of the spectrum is the advection of each gravity wave by the wind caused by all the other winds, by all the others waves. Here is shown the acoustic field calculated by pseudo-differential parabolic equation method developed by Konstantin Avilov. We can see that there are waveguide channels in some atmospheric layers, for instance between heights of 50 and 80 kilometers. These waveguides have finite horizontal extent, and the intensity within these layers significantly increases, whereas in other layers this intensity is very weak. So this so-called effect of intermittency and localization of the infrasound field intensity is caused by multiple scattering of the infrasound field by gravity wave perturbations. Here are shown the vertical profiles of the intensity of infrasound field at different horizontal distances from the source. We can see the vertical oscillations in the infrasound intensity with periods of 2 kilometers or shorter. When filtering these oscillations with periods less than 5 kilometers, we constructed the vertical wave number spectra of these fluctuations at different distances from the source, and we can see that these spectra take very similar shape and decay with decreasing vertical scale of the fluctuations from 2 kilometers to 100 meters with the power close to -3. So this spectra is very similar to the vertical spectra for the effective sound speed fluctuations in the atmosphere. And this is actually the result of scattering, multiple scattering of infrasound field by these gravity wave perturbations. The scattering of infrasound field by gravity wave perturbations also leads to the additional attenuation of the infrasound field intensity with increasing the distance from the source. Compared to the model atmosphere without perturbations, or compared to the model of the atmosphere with only one vertical profile of gravity wave perturbations. We also studied the effect of a fine-scale layer structure of the atmosphere on infrasound signals from fragmentic meteoroids. This work was done in tight cooperation with Elizabeth Silber. We considered two different models of the atmosphere. One model is with varying effective sound speed fluctuations with horizontal distance from the source. Second model is when gravity wave perturbations are concentrated only within stratospheric layer between 37 and 45 kilometer altitudes. This simplified model was taken to isolate the effect of propagation of the acoustic signals through this layer or reflecting from this layer. The partial reflections from this layer is shown in the calculation of the acoustic field from the source, which is at a height of 35 kilometers above ground. This source is below the stratospheric layer with perturbations. We can see that in this case the ray paths have turning points near ground at ranges more than 100 kilometers. So there is a shadow zone between 100 kilometers and 200 kilometers. However, the partial reflections from the gravity wave perturbations in the stratospheric layer and diffraction effects near caustics formed near the ground results in the penetration of infrasound field into this acoustic shadow zone. As a result, there arises a long-lasting tail in time after the main direct arrival of the signal, and this long-lasting tail shown here is obtained due to partial reflection of the signal from the stratospheric layer with perturbations. This tail was found also in the recorded signals shown here, and the correlation analysis of the signals at 3 receivers confirms the existence of this tail, and it maintains its azimuth horizontal phase speed in time, as you can see from the results of correlation analysis. So we found the effects of infrasound intensity, intermittency and localization in some atmospheric layers. The vertical spectra of the intensity oscillation at different distances from the source take a well-defined shape with a mean slope of -3. Also, we found that there is additional attenuation of infrasound field with increasing distance from a source due to its multiple scattering by gravity wave perturbations. The partial reflections of infrasound signals generated by meteoroids caused by fine-scale layered structure in the stratosphere form multiple arrivals and a long-lasting tail in the observed signals. Thank you for your attention.
Thank you very much, Igor, for this very interesting presentation. Igor, you are online, right?
Right, I am online.
Very good, Igor. We got a question from the audience. I will read it for you.
Okay.
The question is, what is your suggestion on how to use these results when analyzing infrasound data for treaty relevant phenomena?
I think that the results of penetration of infrasound field to the shadow zone, when we can detect the source, this is a very interesting result, which is caused by gravity wave perturbations. I think that this may be the application of the results.
Okay, and Ronan, you had a follow-up question?
Yeah, thank you very much. And I was wondering, do you think that it would be possible to, in a few years, maybe to include this in the calculations that are made? You saw very nice calculation, provided that we have sufficient information about the state of the atmosphere?
Yes, of course, we need the current state of the atmosphere to predict the this distribution of the infrasound field. But I think that even if we don't know exactly the real profile, we know the mean real profile, which is not very much differs from time to time, but the gravity wave perturbations have very high gradients, and they actually scatter the infrasound field much more than those gradients in the real mean profile. That's why we of course need the current state of the atmosphere, but we also need the model that of the gravity wave perturbations which will be superimposed on this mean profile.
Thank you very much.
Igor, one final question from the audience. Is ray theory applicable for low frequency acoustic waves, or do you have a modified model?
Of course, this is applicable for low frequency infrasound waves.
Thank you very much. As you know, we have different types of audience, so we are very thankful to you and to all the authors to consider that we may have questions coming from all different angles. So with this, we would like Igor to thank you very much for having submitted your contribution, for being present during the questions and answer sessions, and we look forward to seeing you live in future science and technology conferences. Thank you very much, Igor.
Thank you to you. Thank you.
Thank you. Let's move to the next talk. The title of the next talk is PISCES Updates for Integrating CSS30-like database tables and files into OpsPy workflows. It falls under the theme 3.1. The talk is from Christine Gammons from Los Alamos National Laboratory, Please play the pre-recorded talk.
Hello everyone, my name is Christine Gammons. Today I'm going to be giving a presentation on the updates Jonathan, Brady, and I have made to Pisces, specifically for integrating CSS 3.0 like tables and files into OBSPy workflows. I'd like to start off by noting that going forward, I will be using the term CSS3 databases or database tables to more broadly refer to CSS 3.0, KB Core, and Antelope database tables based off those schemas. Those are the three currently supported by Pisces. I'd like to note many institutions use an expanded schema that includes many of these tables, such as site, origin, event, etc. But Pisces doesn't support every single table in those schemas. Pisces was open sourced in 2014 as a library specifically designed to integrate CSS3 databases into Python codes by defining the tables and columns into objects understood by SQL Alchemy, another open source library designed to interact with databases in general. Pisces also supports the translation of the data and metadata stored in CSS3 databases into OBSPy objects, specifically for integration into Python workflows. Currently, OBSPy streams and response objects are supported, and catalog inventory objects are in development. I was hoping to have those done by the time of this presentation, but everything takes longer than you hope it will. Functionality to convert instrument responses into response objects was added last year and will be the first thing I talk about. Another note I'd like to start with is how I will be referring to instrument response files for the remainder of this presentation. Specifically, I will frequently use the term PASFIR file or PASFIR response to broadly mean instrument response files, including FAT files that are formatted according to the specification defined in the appendix of the 2002 IDC processing manual. This is how we refer to them at Los Alamos. That may not be the case anywhere, so I wanted to make that clear to everyone. On this slide, the figure, you can see a truncated example file. There's some commented header information and then a series of defined stages. The specification supports pole zeros or PAS phases, finite amplitude response or FIR phases, infinite impulse response IIR, and frequency amplitude phase FAP. The file itself contains the shape of the curve, but the actual scaling is of the response for each channel or sensor is stored in the database as the calibration in calib at period in calper as defined in the instrument table, or the calib at period calper in the WOOF disk table. I'd also like to note that many of these files that exist have a group delay stage. However, this stage isn't defined in the 2002 IDC processing manual and has not been added into the Pisces response conversion, though I have plans to do so soon. Since OBSPy is the main Python package used by the seismological community, the goal is to translate PASFIR files and their corresponding database fields into OBSPy response objects, which are a combination of different stage objects. Specifically, PAS stages translate into pole zeros response stages, FIR and IIR translate to coefficient types response phases, and FAP stages into response list response stages, which contain a list of response list element objects, which each contain a single frequency, amplitude, and phase triplet. The instrument sensitivity object is the stage 0 information as defined in the SEED manual, and it includes the total scaling and unit information for the entire response. So it is a combination of all of the gains, normalizations, and the total units, typically from ground motion to counts, for the entirety of the stage. Here I just wanted to show the workflow converting these files, as well as include some technical notes and caveats on the process. You'll note that there is some orange color added to there. I tried to keep the coloring across various workflow diagrams consistent across the slides. That relates to a later slide. The inputs here into the process are shown in green. The dir and the d file in the instrument table give the file location, and this file path, as well as the calib and calper, from the instrument table, the encalib and encalper, are all response into the read passphere function. You can also set the ground motions to output into either meters, nanometers, or pascals. Typically, the database spec for the scaling information is all in nanometers in displacement in CSS3-like databases, but I wanted to give the option to output in meters as well. You can also see that once you have the file, that I show the workflow into the D file location, the inputs into the response object conversion for the read passphere function, and then below that you see the actual response object and what it looks like for this file. Again, I used station A and MO, the station shown in the truncated example file in a previous slide. The sensitivities from all stages are combined into the calibration value in the database. I cannot break them out by stage. What this means is that I set the gain for all stages after stage 1 to 1. And then I set the gain of the first stage, typically pole 0 or FAT, but not always, to the total sensitivity value, and then set that in the instrument sensitivity object or stage 0 object. As a result of these assumptions I have to make, because I can't break them out, you cannot pull out individual stations as independent or truthful on their own. They really need to be left as the entirety of the response object in order to be accurate. I also implemented a passphere file writer that will take a single station XML input, and it will output passphere files for every single response contained in the station XML object, as well as fixed width formatted flat files for the corresponding instrument and sensor tables based on the information in that station XML. Because one station XML file can contain a large number of responses, the file naming for these are fixed. I wanted to note that it would be on the user to change that, as well as to adjust the ID numbers from the flat files if you are going to upload those into a database. But here you can see where the green text box, that is the inventory, is input into this XML to passphere function with some available information about the working directory path and whether you want to write out the tables and what the frequency, all of these would be calculated that if you want it to be consistent or you want it to be different than the frequency for each response in the station XML file. One more note I'd like to make about this slide as well as the last. This is implemented and available through Pisces now, but the API is subject to change. I'm still making some updates, adding some functionality, and some terminology may change. So if you go to use it, just keep that in mind, although there is a deprecation warning whenever you use these functions. Here I wanted to show a comparison of response curves to indicate that the passphere reader works as expected. The graph or the figure on the right shows the response curve from the station XML file for station A and MO from Iris. And the figure on the left shows the response from the passphere file in our database. In this case, the file in our database was converted from the station XML from Iris. But that was done by a different researcher using a different set of codes, giving a little bit of independence to show that this does take the file and convert it correctly. That being said, I do have a note that I had to apply the phase correction manually because, again, I have not implemented the group delay stage, though that is on the list to do this next year, assuming everything goes according to plan. But you can see from the two comparisons that the response curves are effectively the same. The reader will convert the PASPHERE file to an OBSPI object, and this was plotted using the response.plot from OBSPI. And then for the last slide related to the instrument response functionality in Pisces, I just wanted to show that the OBSPI remove response works with this object, and it does produce the same deconvolved waveform effectively. This is from a magnitude 6.5 earthquake in Nevada on May 15th, 2020, as recorded at ANMO. The top waveform is just the response deconvolved in displacement from iris, and then below that shows the response, the deconvolved waveform using the PASPHERE response at LANL overlaid on top of the iris waveform, and there's effectively no difference, though if you were to scroll in, you may see some small differences, but they are effectively identical. The next two slides show the in-development work on the inventory and catalog objects. Figures on both slides show a rough workflow for translating CSS3 database tables into these objects, which are structured around the FDSN specification. As a result, some adjustments have to be made. For the inventory object specifically, if a network code is not provided for each station, the network is set to a double underscore, which I chose because the double underscore does not conflict with any existing network codes. And if a user exports waveforms or station XML files based on the ID, the file name will not start with a period and become a hidden file. Also, there are no location codes as they are not contained. Location codes are not contained in the CSS3 family of schemas. Pisces will convert what is in the database as it is in the database. Particularly, for example, around location codes, we at LANL often append the location code to the channel to get around that limitation. And as a result, this is how the location code will appear in the inventory object. Catalog objects have fewer adjustments as a result of differences between QuakeML and CSS3 specifications, but some of the terminology is different. For example, a catalog object pick is equivalent to a CSS3 arrival, and a catalog arrival is equivalent to a CSS3 ASOC field. CSS3 also has a different set of event types and associated codes, so a translation layer is added within Pisces to ensure the output is consistent with the FDSN specifications. To summarize this presentation, Pisces is being actively updated and maintained. The recent additions include read and write capabilities for instrument response files. Inventory and catalog support are in development. We also have some longer-term plans that are not shown here, including improving the Pisces backend to be more agnostic, to include more agnostic data typing using Libra, another LANL data management package open sourced in 2024 that adds in support for multiple schemas based on some definition of those schemas within tables. And then lastly, we are looking to add web service interfacing support for schemas supported by Pisces, essentially KB core web services similar to an FDSN web services, but supporting the KB core and CSS3 family specifications. Thank you. Let me know if you have any questions.
Thank you.
Thank you very much, Christine. Christine, you are online, right?
Yes, I am here.
Thank you so much for joining us, and thank you for this amazing work that you just presented. We're waiting for questions from the audience. One question from our side is, could you please tell us about the benefit of this improvement? What does it mean in terms of time saving and so on?
It'll let researchers go directly from database tables to these OBSPy objects, since that is kind of the primary Python, open source Python package seismologists use. The idea is that once this piece is complete, it'll go into a larger function that you can treat similar to an FDSN web services, where you can put in station information and it'll pop out an inventory, and you don't have to go through and extract all of the information from the query from the database yourself.
Very good, very good. Thank you for that. In addition, we got already some questions from the audience. I will read it for you.
Mhm.
So a member of the audience thanks you for the presentation. And this person says, while the group delay for FIR stage is relatively straightforward, how would you estimate the group delay for the PAZ stage when the phase response is nonlinear?
I don't have a good answer for that. Right now, that is a bit beyond the scope of what I'm trying to do. I am trying to convert files exactly as I get them, because there's not a defined spec that I can find. If someone has one, please send it to me. For the group delay, I have to go through and find enough files and make sure that the delay is behaving the way I think it is. Because if you go through the seed manual, many times the digitizer will anticipate the delay, so it'll actually timestamp the samples to account for it, and I want to make sure everything is behaving the way I believe it to be. So without a defined spec right now, I just need to go through and find enough files and test it and make sure it does what I think it does. In terms of estimating it from the past stage, that would be a much further out question beyond just getting these converted directly.
Well, I mean, for sure, people will contact you because we are being flooded by questions about your presentation.
Okay.
So, Ronan, would you like to read another one?
Yeah, we have another question from the audience. Thanks, Christine, for your presentation. That's within the question. And providing an important code allowing to convert CSS formatted data to the FDSN standards. Could you say something about the waveform functionality within PySys?
So right now, the waveform functionality is the most complete. I was hoping to have some of this more done by this presentation, but time being what it is, that will, if you know how to format set up the Pisces tables and kind of format the queries, there is a woof disk to trace function that for every query that comes out of that woof disk table, it will create a trace in a stream for every woof disk entry. The nice thing about the inventory stuff is that once all of that is complete, it'll also be able to potentially grab responses or build an inventory so those can be directly attached using the existing OBSPy functionality.
Thanks very much.
Thank you, Chris. One final question from my side, and then what we will do is we will send you all the questions that we're getting so you can review them. So the question, I'm a passionate myself about data, and the question is about database. So does PySys include any consistency check to spot possible errors in the databases?
Not really. That is a recognized need. We are working on a different data management package that we've open sourced called Libra that we are imagining will have some QC plugins that can do some basic checks, but we are still in the planning stages around that, and I can't make a guess exactly when that will release. Although Libra, which is like a schema manager type package, where if you put in the schema, the defined tables in a specific format, it will be able to dynamically create the SQL Alchemy ORM objects for that schema, like Pisces does for CSS3, but Pisces currently has it hard-coded under the hood versus doing it dynamically.
Fascinating. Everybody who has sent a question online, we say thank you. You all can access Christine's presentation online. And what we will do also is that there you can have all your, you can have Christine's email, and we'll forward to Christine all these questions. So Christine, thank you very much for your time. Thank you very much for your contribution and for being here today with us.
Thank you. Happy to do so.
Thank you so much. With this, we move to oral presentation number 3. Right now, we will play the pre-recorded talk from Heli Desai from the University of Cambridge. I see that she's online, so we will also have the possibility of asking Heli questions. But first, we'll play the presentation called Tech for Tolerance, using gamification to drive youth engagement in the Nuclear Test Ban Treaty. Please play the pre-recorded talk. Thank you.
Dear Excellencies, distinguished guests, colleagues, and friends, it's an honor to address you here today at the Science and Technology Conference 2025 with the Comprehensive Test Ban Treaty Organization. Today, with this opportunity, I wish to speak not only about the treaties and verification, but about the youth who is going to inherit this treaty, this mission, and this responsibility of taking it forward. We already obviously know that the CTBT is critical, especially in this time and age of proliferation. We know that science of verification is very robust. We also know that the humanitarian case is fairly overwhelming. And yet, the political momentum towards universal ratification has slowed down incredibly. In many parts of the world, young people are absolutely unaware of the treaty's existence, let alone get engaged in its defense. So this essentially is a critical problem which is at hand. How do we involve, inspire, empower the next generation to take ownership of the CTBT? And this is quite a paradox as well, because young people care profoundly about the future of the planet. You'll see young activists taking initiatives for nature, AI, tech, climate. But when it comes to nuclear issues, what I understand or what I believe is that the language, the systems, technicalities, and the complexity create barriers that leave them feeling excluded. So the central problem, or the question here becomes, how do we bridge this gap? How do we transform something that's as technical and as specialized as, say, nuclear test verification into something that excites, educates young people, young leaders? So my proposal today is one of the most powerful tools that potentially we could use, that the youth is already involved in, is gamification. Now, I say why gamification. So let me just first be clear that when I say gamification, I do not mean trivialization. I do not mean reducing nuclear verification to just entertainment. I mean applying the tested mechanics of game design to challenges, rewards, competition, cooperation, storytelling, immersion even, to build experiences that make the CTBT real, engaging, and empowering for young people. Because games are essentially not passive. They require active participation, and participation is precisely what we need from the youth. So consider the psychology. When a person plays a game, they're motivated by sort of curiosity, by achievement, collaboration, and also the sociology. That is, games create a sense of community. Online games bring together millions of people across the border, language barriers, barring cultures. They build trust, collaboration, and a sort of sense of a shared purpose. But what this gamification could look like for the CTBT, which would this would require us to sort of move from theory to practice. So let's say, for example, a seismic detective game wherein you log into a platform and you see real seismic data from the IMS. The challenge would be then to determine whether the signal represents an earthquake or a possible nuclear test. The gamers then soon learn to recognize telltale differences in waveforms. With each correct answer, they progress. Soon they're analyzing hydroacoustic data from oceans, infrasound signals, from the atmosphere, radionuclides from the air. They're not just playing, but they're then acquiring real verification skills. This could also be used in, imagine, augmented reality sections. There could be an AV headset with a suspected test site. Now they must deploy geophysical sensors, collect soil samples, test isotopes, follow strict verification protocols within the game, where every step mirrors the procedures of real on site inspections. And for the player, it feels like a mission. For the CTBTO, it becomes training awareness and capacity building. This could also mean a diplomatic crisis simulation, which is conducted online. Teams of young people take on roles as diplomats, scientists, journalists, civil society leaders. A suspicious event has been detected. Do they call for an on site inspection? Do they release the data publicly? How do they balance scientific caution with political urgency? In this game, perhaps players experience complexities of diplomacy firsthand. They learn that verification is not only technical, but also very deeply political. Then, for another example, a global nuclear risk mapping simulation could also be an example. Teams from across the world use satellite imagery, historical data, political analysis to identify potential test sites. They debate risks, weigh probabilities, and corroborate borders. Such a platform would not only then teach about verification, but also foster the habits of global citizenship and cooperation that CTVT then sort of embodies. Each of this model builds on technologies and approaches already used elsewhere. And each of them has the potential to sort of transform young people to engage with the CTVT. Another one of the proposals that I initially had in mind was also a CTVT youth gamification of a hub of sorts. And since the CYG is already engaged in many, many activities, this could also be one of them. This would essentially be a digital platform that's integrated with the CTVTO youth group. It would offer sort of a suite of gamified learning tools, data challenges, AR inspections, crisis simulations, like I said, collaborative mapping. And it would be multilingual, adaptive to sort of different skill levels, and accessible from everywhere in the world. So participants essentially earn digital badges or micro certificates or recognition for their skills, which they could also showcase through progress of their universities, even within the governments. Collaborations with foreign embassies could happen to take this sort of on a global stage. And the CTVTO could not only use this hub for education, but also to identify and mentor the next generation of verification experts over time. The hub would not obviously replace traditional training. Rather, it would be supplement to sort of opening doors for youth who otherwise lack access to such platforms or such activities or such information in general. It would also transform the CTVT from a distant treaty to a lived experience for the youth that it so eagerly wants to involve in its activism. And to realize this vision, I believe we would need a number of things. First would be partnerships. The CTBTO should, like I said, collaborate with universities, educational technology companies, NGOs, embassies. Many of the technical tools already do exist, from an AI-driven anomaly detection to sort of AR learning platforms. A task would just be then to adapt them for verification. Second would be a lot of pilot projects that need to be laid, a blueprint for which needs to be laid out. We don't obviously need to build the entire thing immediately. A small pilot, say an IMS data classification challenge, could be developed, tested with a handful of students, and then refined and worked on over time. Success would eventually build momentum, of course. Third is, of course, resources, both financial and institutional. We must recognize that gamification is not a gimmick, but a legitimate tool for capacity building, and then eventually promote it like that. And finally, co-creation with youth, I believe. Because the most successful games are those built with their intended audiences. We could invite youth not only to play, but also to design. Basically, hackathons, design sprints, collabs could bring creativity into the process and also get them involved while doing it. And we're obviously not starting from ground zero. There have been precedents that we can learn from. For example, I think the game Folded engaged ordinary citizens in solving protein folding puzzles, which within weeks, then they discovered new structures that advanced HIV research. Duolingo, of course, has shown that gamified learning can attract 500 million users worldwide to learn different languages, making language acquisition accessible and engaging. I think politically and more security-oriented activities have also included NATO's Lock Shield cyber exercise that demonstrates how immersive gamified scenarios can train experts even to respond to real-world crisis. Thousands of professionals are tested annually in this virtual battlefield, right? In our own field, tools like, say, Nuke Map have shown that even interactive visualization could reach millions by allowing people to simulate nuclear explosions over their own cities, other cities. Nuke Map, by I think Alex Wellerstein, is it, has made abstract consequences of nuclear weapons immediate and quite personal. Each of these cases just prove a simple point that when information becomes experience, people start caring. They learn, remember, and sort of act even. So then why does this matter for the CTBT? Is that the treaty is essentially not just about banning nuclear tests. It's also about building a culture of trust and verification and cooperation. And that culture cannot survive if it remains confined to diplomats and scientists or policymakers alone. Must be embraced by citizens, especially by the youth who's going to take this forward. And I believe gamification would offer us a way to cultivate that structure. It could transform verification from an abstract process to a very shared experience, equipping sort of young people with both technical skills and political awareness. It could foster collaboration, like I said, across borders, languages, disciplines, and create sort of a pipeline of leaders who will then champion the CTBT long after this exercise has ended. So, I mean, what I believe for the path forward, CTBT could convene like a gamification hackathon, invite youth worldwide to design mini games around verification concepts. This would not only generate ideas, but also signal that their voices really matter. Then they could develop like a pilot game, like I said, with seismic classification challenges using IMS data, tested on students with the CTBTO youth group who essentially are already indicating an inclination, sort of a motivation to talk about this, gather feedback from them and improve. Step 3 could be to expand a full hub with multiple modules from AR inspections to diplomatic simulations, make it multilingual, make it adaptive. There could be an integrated mentorship from experts, diplomats, scientists across the world involved with the CTBTO. And then we could institutionalize the hub within the CTBTO outreach and training programs. Let it become a part of the organization's long-term strategy for youth engagement. I mean, I believe this path is very, very ambitious, but with the right amount of effort and energy, it could also be very realistic. And the potential payoff could just be incredible. I'll just leave you with that. Thank you so much.
Thank you very much, Heli, for this presentation. Heli, you're all right, online, right?
Yes.
Very good. Thank you once again. Very, very interesting concept. And we got a question online for you. And it's a question probably from one of our trainees in the on-site inspection division. And the question says the following. For on-site inspections, there are already developed training modules that use your gamification approach. So they are already in step 4 in your path forward. Are you aware about this? And if not, how would you suggest that the CTBTO makes such training modules available to the youth and to the general audience?
Yeah, thank you so much for the question. And this is also very much in line with the question that you posed initially, right? It's basically about getting things out there. So while I was aware about this, I have interacted with a lot of young people who are not aware of such initiatives. And so, what I would propose to get the youth involved in such gamification activities would primarily be like interactive challenges on social media that the youth can be a part of to engage broader audiences. Get celebrities who sort of endorse, advocate peace, science, education to showcase the game. Their endorsement could broaden the reach beyond academic and policy communities to sort of make the case for CTBTO and make the activism sort of more global than it already is. Sort of try global youth hackathons where participants could use the game to tackle simulated nuclear challenges that you say you already have in the developments and in the works. This would sort of encourage creative problem solving while building youth networks around the CTBT's mission. There could be events and competitions that are held that could sort of popularize the things that are already in the running, and then eventually could soft launch the new games or new activities that the CTBT has to sort of get it to a much broader audiences. You could also sort of try and participate in partnerships with universities and think tanks who are into nuclear research, who are into sort of nuclear testing, physics labs maybe, to invite more participants. Basically, educational positioning of the gamification of CTBT would sort of be the first step ahead. And then we could move on to sort of games and competitions or hackathons or getting celebrities involved on social media and whatnot.
Thank you. I like a lot what you said about educational positioning. It's very, very, very relevant. Absolutely. Ronan, there is another question.
There is another question from the audience, and the question is, what could be the duration for implementing the whole gamification system from end to end?
I'm sorry, I didn't quite catch that.
It's what could be the duration? How long would it take to implement the whole gamification system?
So it depends on how you take it, right? So it could be done in phases. So initially, the pilot or the soft launch phase, once the entirety of the game is ready, that you completely trust in that this is a game that we want to launch out in the public as sort of the face of gamification of the CTBT. That could take around 3 to 4 months on social media. Test it out with a small group. Partner with a university, educationally position it, see how it's received. Then you sort of move on to the main campaign, receiving and incorporating feedback from how the pilot launch or the soft launch has been taken, has been received by the students. And the main launch would then sort of include hackathons or social media campaigning, like we spoke about. So this would sort of broaden the horizons and keep the momentum steady without the audience getting fatigued, and then sort of sustain and integrate into ongoing yearly cycles that the youth would look forward to. So then sort of launch a fellowship or an annual yearly hackathon that students or kids could participate in and sort of look forward to then every year. This could also have reward systems like a visit to the CTBT or a fully funded fellowship to sort of take a month worth of a sort of summer research program in Vienna that students could experience, come to Vienna and experience it for themselves, or something of that sort. So eventually, I mean, it just depends upon how you just how you mark the phases. So it could be a three phase system that could sort of end in 1 year, and at the end of the year, that you could sort of analyze and then process what's going right, what's going wrong, what do we need to change for for the people to process it better or receive it better.
Thanks very much, Ellie, for your comprehensive answer. Thank you very much.
Thank you. There are more questions. Once again, we will send you all these questions via email.
Of course, please do.
Yeah, all in the audience who have submitted questions, please understand that we have a limited time to ask questions. You have Ellie's email address in her contribution, so please also feel free to send her a note and ask directly these questions. Ellie, thanks a million for joining us.
Thank you so much. Honored to be here.
Yeah, and see you in person in future science and technology conferences.
Absolutely. Thank you so much. Looking forward to it. Looking forward to more of your questions as well. Thank you.
All the best. The next talk, we move now towards atmospheric transport of radionuclides using physics-based and machine learning models. The contribution, the author, is Akshay Govardhan from Lawrence Livermore National Lab. He's not in the room at this moment, so let's play the contribution and see whether he joins us after the contribution. So please play the contribution. Thank you.
Hi, this is Akshay Govardhan from Lawrence Livermore National Lab, United States of America, and I'm going to talk about subsurface to atmospheric transport model of radionuclides using physics-based and machine learning models. So how do we connect a subsurface transport model to atmospheric model to understand the propagation of radionuclides in atmosphere coming out from the surface? So to understand this, we are planning to connect two different models. One is a subsurface model and one is the atmospheric transport model. So I'm going to talk about the atmospheric transport model, AOLIS. AOLIS is an atmospheric simulation tool. It's a very high fidelity tool, and it's based on the work done at University of Utah, Los Alamos National Lab, and Lawrence National Lab. And it's a fast running computational fluid dynamics model. It's an efficient 3D CFD model based on finite volume and can predict transport and dispersion of contaminants in urban areas as well as complex terrain. And this is really important in this case because one of the main idea of connecting the subsurface transport model to atmospheric transport model is to detect the transport of radionuclides from an underground nuclear test, right? So for that, we need to have a model, atmospheric model, which can work in complex terrain, because most of these regions where these underground nuclear test happens are really complex terrain region. So apart from that, this model is also coupled with the Lagrangian dispersion model, which can predict dispersion of particles of different sizes and their subsequent deposition on building as well as ground, right? And we have integrated different data sets for this model. So this is a really nice model. It's really easy to run. It requires minimal input to run. All the user needs is input latitude and longitude of the release location, and the system automatically converts a grid using the information from the terrain as well as the building database. And we have the building database of more than 100 cities already in our database, so that we can easily query any city and build a grid for that region. As I mentioned, it's also connected to the other data set. Like on the top left, you can see the meteorological field option. It's HRR is one of the most common option which is used to run the model as input. We can also use ECMWF, WRF, or GFS, whatever is needed, we can use that. Apart from that, it also have land use database integrated. Even in a small region, in an urban area, say, there might be a big park or a lake or a pond. So you need to account for these differences. So we have integrated this kind of high resolution land characteristics data with the model. Also, when you need to determine deposition, this land use characteristics come in very handy to determine how the deposition is going to take place. And we also have population databases integrated in the model, as well as global soil maps from all around the world. We have done our due diligence. We have validated our model with existing data. So this is the case for complex terrain. You can see there is a hill in the middle of the domain, and along the cross section of the hill, along the flow line, there were a lot of measurements taken at two different lines, line A and line AA, here shown in the top left figure. And the circles, the symbol shows the data point, and the black line is the model produced AOLIS results for this scenario. And as you can see, it compares really well with the model, and also as compared to other models like WRF, we are trying to compare our results with other models too, and it's doing a great job. And we have published this result in our paper in Atmosphere Journal in 2021. So this was the model, and we wanted to validate our model for more use, like for real-time xenon sensor. Can we actually use this model for predicting how transport is going to happen from xenon, and these sensors are there, so can we produce good results, right? For that, in the LYNM project, there was a React 22 campaign where they were planning to release xenon, and there were a lot of sensors around the p-tunnel region. So the first part of the project was they wanted to design the field campaign. Since we were confident about the model, we had already validated our model for complex terrain region and other dispersion studies. We decided to help them plan or design the experiment, right? So for the React 22 model campaign, we ran a bunch of Aeolus simulations and recorded results, contaminant predictions at different regions, so that they can assess how much source they need and where to keep the sensors. So for that, we made a vast tool. It's called Atmospheric Simulation Testbed, and where we ran Aeolus multiple times. You can see for different wind direction, different wind speeds, different stability, different release location, different release duration, and all this data was produced in and kept in this Jupyter notebook format, where the experimentalist, they were able to access this data, and that helped them design their experiment. So where should they keep the instruments or the sensors, right? And once this was done, the experiment happened. This is just one of the example 3D simulation done by Aeolus, and due to the complex terrain, you can see even small change in release location can lead to really different dispersion pattern, right? So that's why you need a model which can account for these kind of complex terrain features. So once the experiment happened and we had this rich data set coming out from React 22, now it was our turn to validate our model, like how well does it compare with the React 22 data set. So a lot of campaigns happen during React 22 campaign, but we focused on one specific campaign, React 04, where there were 4 real-time xenon sensors and 1 gas sampler in closer in position, and and there were 8 positive hits within 2 kilometers, right? So this is the scheme. So you can see this is the release location on the real top of the scenario. The green one shows detect, the red one shows non-detect, and the blue one shows detect as well as the gas sampler detect. So this was the data coming out from the React 04, and this was the Aeolus simulation which did for all the React campaigns: React 01, React 02, React 03, and React 04. And as I mentioned, we chose React 04 for our validation. We went in depth. So React 04, you can see the location. The release was Apron 4, and the wind speed was 6.23 meter per second, and the wind direction was almost coming out from north. Stable conditions and a really shallow boundary layer height, right? So we input all these things, but the results were not optimal. And the reason why we looked at it and like why the results were not optimal, because the wind conditions given to us, these were with which we drove our model, were at the release location. And I can see from the map, the release location is surrounded by a lot of mountains, a lot of hills. So that release wind speed and wind direction is not representative of the whole domain. And it is actually heavily influenced by the surrounding terrain. So that's why we decided to look at different monitoring towers and identified tower MT01, which was situated on the mesa top, away from any kind of canyons or any kind of complex terrain regions. And when we plugged in our data with that model, the results actually improved a lot. And I can show you some results here. So after we use the right wind condition, the black line is the data, and the red line is the simulation. And you can see the arrival and departure of the plume is really well predicted by the model, and the peaks are also really well predicted. These are all in linear scale, not in log scale. Usually all the validation you're used to seeing log scale. But since this is not a log scale, linear scale, it looks log, but actually it is really good. So this was done, and now this was all about the atmospheric model, and now I'm going to talk about how we are coupling the subsurface transport model to this atmospheric transport model, Aeolus, right? So as I mentioned, radionuclides produced from UNEs can slowly migrate to the subsurface and vent to the atmosphere, where they're transported and detected downwards. And these all regions are located in remote areas surrounded by complex terrain features and greatly affect the detectability of radionuclides once they reach the atmosphere, right? So that's why there is also a part of this project we are going to do a field experiment to validate this subsurface to atmospheric transport model, SATIX, where they're going to release some stuff underground and the contaminant is going to come out through the cracks, and it will be detected downwind in this complex terrain region, right, to understand this, because we are going to couple a model, develop a model, but we need data to validate model. So this SATIX experiment is going to happen, and where we're going to use the data from this experiment to validate our model. So what are the models we are going to use? As I mentioned, we are going to use Aeolus at the atmospheric simulation tool, which is really high resolution model, can account for all the complex terrain region, urban areas, everything. And the NUFT is the versatile subsurface transport model, which can give us probabilistic xenon fluxes generated from subsurface transport model. Here you can see some of the figures over the time, how the xenon subsurface model produces the data, and how these concentration increases and decreases during the period of days. So the idea, since you must have seen that the xenon is emitted from the surface over days, right? So that's a long period, and we can't use this kind of CFD high resolution model to simulate something for 30-day period. So what we did was we are going to use ensembles of Aeolus model and feed these ensemble like for different wind condition, for different wind speed, since we had the experiment from the VAST I mentioned before, and we are producing we produce an ensemble of more than 2,000 Aeolus simulations. Here are the individual maps, and then feed it to a machine learning module. Input is coming from the surface transport model, so this acts like source, and when we combine the input with the machine learning module, which has this ensemble 2,000 ensemble of Aeolus runs, we can produce a machine learning model output of how the concentration will be in this region, and that result can be compared with the data, with field data. So this is our approach of quickly, rapidly predicting how the contaminants are going to transport over days, using really high fidelity model, machine learning, artificial intelligence, and this combining the best of best and producing a credible results. And this is where we are at. We have produced this model, and we are waiting to validate our model now with the data. So as I mentioned, Aeolus large simulation model was successfully validated, was used and successfully validated for React 22 sensor design. Validation was done using the same data, so it is really good. Like, we could use the model to design the experiment, and at the same time we can use it to validate, use that data to validate our model. So and in this thing, what we learned was the conventional understanding was to use the meteorological condition at the source location. A lot of time we do that, but that understanding is not right, especially in complex terrain region, because that can lead to suboptimal performance of the model, because that's not the right inflow condition for the whole domain. It's greatly influenced by the local terrain, so you need to be careful. And also we develop a machine learning module which can rapidly simulate atmospheric dispersion of radionuclides arising from an underground nuclear test by coupling Aeolus with output from a subsurface transport model, NUFT. So yeah, if you have any question, you can email me at goarden1@llnl.gov, and thank you for listening.
Concludes the presentation from Akshay Govardhan. He's not online, but as we said for the previous authors, if you have any question, please check Mr. Govardhan's presentation on the platform. You will have his email address there, and please send all your questions to Akshay Govardhan, to whom we thank, even if he's not here. So now I give the floor to Ronan, who will moderate the second part.
Good afternoon, good morning. So the next talk is about explosion discrimination, and the title is Limits of Explosion Discrimination for Monitoring Efforts with Machine Learning. And this is given by Luisa Barama from Lawrence Livermore National Labs. Luisa is online, so she will be able to answer questions later on. The floor is yours, Luisa.
Please play.
Hello, my name is Luisa Barama. I'm a postdoc at Lawrence Livermore National Lab, and today I'm going to talk to you about ongoing work on global and regional underground nuclear explosion discrimination with machine learning, and ways that we're looking to improve existing models and combine existing models by adding seismology-led and physics-based features. The three goals of the work that I'm showing today was looking at the transportability of global models to regional distances, making use of legacy underground nuclear explosion data, and looking more at the impact of adding features to our training data. I also want to apologize. My slides are in the format for a poster. There was a bit of a miscommunication of whether or not my virtual presentation would be a poster or oral slides. So my presentation is in a poster format, but I've zoomed into certain sections to hopefully make it easier to follow. So I thank you for your patience on that. So let's first take a look at the data. Plotted here in red are the underground nuclear explosions used in the training data set. All of the holdout underground nuclear explosions are in yellow, and all of the triangles denote seismic stations with color denoting what institute that data is sourced from. Now, to generate this list and to compile this data, we first started with a digitized comprehensive list of 2,174 declassified nuclear events reported globally. These two reports we sourced this information from were from the Defense Research Establishment and Stockholm International Peace Research Institute, and a report from the Department of Energy in the United States. For the North Korean tests, we used the USGS reported origin time and coordinates. We only wanted to include underground events, so that narrowed down all of our explosions to 778 events that were detonated either in shaft, tunnel, gallery, mine, or buried, and also had waveforms available. Then we made this training data set, reformatted in a way that's easy to use not just for seismologists, but also data scientists interested in exploring machine learning for this problem. And we published this data set in 2022, and it's now available on GitHub and Zenodo. On the left-hand side here, we have two example waveforms. The top is from an earthquake, the bottom is from an underground nuclear explosion, and the white trace there is just an example of what a 1-minute cut of that segment looked like. For development of our global underground nuclear explosion discriminator, we tested with a variety of different window lengths. We finalized on 20 seconds long. And we found high accuracy when both training on only historical data, which included formerly analog and then digitized data, and applied it solely on the more recent North Korean tests, and vice versa. In order to fine-tune the global discriminator that included a lot of teleseismic data, we narrowed the distance range down to 20 distance degrees. So plotted here, we're just showing the distribution of data with station epicentral distance degrees, and we cut off the range of distances to 20 degrees, and we're just showing here that we were able to do that without removing too much of the data that we had. So there's a bit of limitations when we're looking at explosion data. There's especially for underground nuclear explosions, there's many repeated test locations and emplacement conditions. To address this limitation, the training and testing data, we separated it by unique source and location so that we weren't, repeating on a lot of different sources. We treated those unique, location and station were really just the emplacement condition testing locations. We didn't want to train on the same location tests and then test on those. So we're trying to remove that bias. We have data specifications. We used distances from 5 to 20 epicentral distance degrees. P-wave seismograms that range from 20 to 60 seconds. We ended up, for the final model of the results I'm showing today, we used 20-second seismograms, and we bandpass filtered from 1 to 5 hertz. For each of the waveforms included in training, we had corresponding features that we calculated. Those included the dominant frequency content of the trace and signal-to-noise ratio at 2 different frequency bands, a high and a low. We included polarity and the P-wave decay or slope. So our pre-processing and signal-to-noise ratio already does decrease the number of samples that we can include in training, but also limiting data to only regional distances also decreased our training data samples to around 10,000, a little less than 10,000 samples. To increase this, we used data augmentation, and what we did was, rather than have a fixed point in time within our 20-second window of where the P arrival is, we allowed there to be variability and flexibility of where that was. So for a single trace, we had 3 different iterations of that waveform with a randomly selected point in time within the window of where the P arrival is. So this is a way to really boost the number of training samples that we had and stabilize our training. Now we're going to take a look at our model architecture. So we combined our 2023 global convolutional neural network that was a 3-class output. So output of earthquake, nuclear explosion, or noise. Then we combined it with the 2-branch model from Kong et al. In 2022, where they combined the powerful features of a convolutional neural network with physics parameters and had a 2-class output where they focused on chemical explosion or natural earthquake at more local distances. Now, convolutional neural networks can be applied to 1D time series by sliding this 1D convolutional filter across an axis to detect local patterns, for example, peaks, dips, oscillations, or features that are like an impulsive P arrival for an explosion or a non-so-impulsive arrival of an earthquake. And we can pool all of these together into a dense layer that then aggregates all of the learned features to perform regression or classification that are shift invariant, which makes them really useful for discrimination and classification tasks. So when we're looking at the 2-branch model from Kong et al. On the right-hand side, the blue dotted box is the deep learning branch, which takes in waveforms as the input, with the convolutional neural network layers as the hidden layers, and a fully connected layer to flatten out the features. The green box on the bottom contains the physics-based features, where we include all of the features that we're including alongside the waveforms. The features from these 2 branches are then concatenated and pass to another fully connected layer to make the final decision of explosion, earthquake, or noise. So looking at the results of our model, we plotted here as the earthquake accuracy in blue and underground nuclear explosion accuracy in orange. For the global model, where we had a large range of distances, teleseismic and regional all combined together, our results center around 90%. For when we're incorporating our waveforms and features, we improved that model accuracy up to centering around 95%. And when we focus down to just regional waveforms, then we have limited improvement of the model up to about 96%. We can kind of explain this with there's more variability in the the waveforms that are across a large distance range, to teleseismic range. And so focusing down to just the regional waveforms, we have more consistency across our measurements. But on the whole, this is an encouraging result, so showing that incorporating additional features does improve our model robustness. And for our ongoing work, we're evaluating the impact of additional component data, such as multiple frequency bands and quota envelopes, to further enhance our model performance beyond single frequency band or raw data approaches. We're also comparing conventional methods of explosion discrimination, like P to S ratios, and seeing if there's advantages of machine learning models when these conventional methods have less confidence results, or where our classification confidence is low. But with that, I want to thank you for your time, and I'm happy to take any questions during the live session, or feel free to email questions to me at my last name, barama1@llnl.gov. So thank you for your time today.
Thank you very much, Luisa. We do have one question, and the question that we have is, would you expand a little bit on the data augmentation process?
Yes, of course. So the data augmentation that we did here was actually pretty simple. We narrowed down what length of window we wanted to train the model of for all of the seismograms or all the time series data. And so we just, set a random, built a quick random algorithm to say, okay, we need, from this one single trace, we then allow the P arrival for the earthquake or underground nuclear explosion to arrive anywhere within that window, allowing for at least 5 seconds of signal. So that meant for a 20-second window, it could arrive. You could have the P arrival at up to 15 seconds. So we had 5 seconds of P arrival signal, but it could occur anywhere within the window. I think we had a buffer of 2 seconds. So it's from 2 seconds to 15 seconds that P arrival could arrive anywhere within that window. So this is actually pretty simple data augmentation, where for each single trace, we had 3 different cuts of that data. So, what we see here is that this reduces the overfitting. So by exposing the model to this wider variety of data, this augmentation can then prevent it from memorizing specific characteristics of the training data. So here, if we had, before this, we had set that the P arrival was always at 5 seconds within the window, or 10 seconds if we were using a 1 minute long seismogram. And this actually, when we did see that, for one, you have less data to train the model on, which makes it a little less stable. But then when we applied the model on a continuous data stream, we actually saw a lot of flipping of the model predictive confidence of whether or not it was an earthquake or explosion. There was a lot of variability, especially right before the P arrival. And when we did do this applied data augmentation, you're preventing the model from learning that, at 5 seconds is when I should see a signal. So you're actually, you're kind of preparing the model for more diverse scenarios. So you're making the model better, but also at the same time, you're stabilizing the training also by kind of increasing this kind of artificial increasing of your data. And there's other things that we could have done, is also adding noise into the data. So there's other things that we could do to make small modulations to the training data to also boost the amount of data. I hope that answers your question.
Thank you very much, Luisa.
Yes,
Thank you.
Luisa, indeed. I mean, it's very robust, the system that you are applying. And we got another question from the audience that is on the same page. So they thank you for your interesting talk. And I will read. I was wondering what common features across all the training waveforms allow your algorithm to identify a new event from a different location. So what common features across all the training waveforms? Luisa, you're muted.
Oh, I am so sorry. I had muted myself again. Thank you for your question. We actually had some pretty simple features. So the convolutional neural network part of the model architecture identifies the parts of the stream that are unique and also consistent for each training division. So there we have whatever the machine is able to recognize using those convolutional filters. So identifying what maybe is harder for us to identify that is consistent and unique across all earthquakes, P arrivals, or all explosion arrivals. And then the features that we added in for right now, we actually, for this model, we didn't include P and S ratios. We were focused really on trying to focus on the P arrivals, but we were also looking at the signal to noise ratio and the ratio of energy in the seismogram at lower frequency bands compared to those at higher frequency bands. And explosion data is often more emergent in the explosion data at higher frequency bands. Then we're also looking at the coda slope and then the overall energy. So that's the square of the velocity seismograms of that P arrival. So those were the features. I actually don't have an answer for which features were the most useful for making the determination, but that's definitely something in our continued and ongoing work of using a random forest and doing some feature ranking to see what's the most useful in making our determinations. I hope that answers that question.
Thank you very much. I think we will. Thank you very much for your answers, Luis. I will move now to the next talk, which is about predictive maintenance, and the title is Towards Predictive Maintenance Strategy through Waveform Anomaly Detection Using Unsupervised Learning. And the talk is given by Jun-Ting Lin from Lawrence Livermore Laboratories. Let's play the video, please.
Hi everyone, my name is Tim Lin. I'm from Lawrence Livermore National Laboratory. And today I'll be talking about our work on waveform anomaly detection using machine learning. And the goal is to build a predictive maintenance strategy for a seismic network. So the motivation of this study is that we have a gigantic network, the International Monitoring System. And we need to ensure the data are in good quality for event monitoring purposes. So the station maintenance is very important. However, station maintenance is very expensive as it involves money, time, and human effort. And also, if you look at the plots over here, you can see that those are the scheduled maintenance. And not all of these are associated with the actual instrument failure. So for example, if you look at the time series plot over here, these are the 30 days of continuous time series data. And you can see that it's not associated with the instrument failure. So the question is, can we make the maintenance more effectively? So there are basically three types of different maintenance strategy. And the first one is called a run to failure. And you can see that this is the original data quality. But over time, the instrument degraded, and then eventually we have this failure and the data loss. So that we have to go to the field and fix the problem and bring this data back to the original standard. And the second one is called the preventive maintenance, and this is also called the scheduled maintenance, and which ensure the data is always in good quality. But however, they are perhaps more servicing than the actual needed. And the last one, which is our goal, is called predictive maintenance. And the idea is if we can detect this subtle degradation type of signals, and then we can make a plan beforehand so that we are not too late to have data loss, and also we can save some money for the unnecessary maintenance over here. So there are, however, challenges in detecting degradation signals. And the first is that the anomalies can be anything. There's no clear definition if you look at the figures. And also the signals may be subtle and hidden within the data. So without telling you that this is a anomalous signals, it's very hard to tell from just looking at the time series data. And the way that we know this is true is to compare it with the neighboring station, and we see there these missing signals over here. And also, there's no ground truth data to learn or to compare. So we propose to use this unsupervised learning model, the autoencoder model. And the idea of autoencoder is that it compresses this information into a lower dimensional space. And then a decoder will decode this information back to the original waveform. And by training the model with a lot of seismic data, it learns what are the most important or the common features that needed to represent seismic data. And we can compare the input and output using the correlation coefficients. So we can use this value as a proxy of the data quality. And the good things about this structure is that there's no assumptions on anomaly signals. And also we can explore the information in seismic waveform. So we train the model with the USMS data. And we basically download 8 years of continuous data for all these networks. And then we downsampling it to 1 Hertz and cut that into in hourly chunks. And we split more than 5,000 days of time series data into the training, validation, and testing data sets. So after training, we can now test the model performance. You can see that this is a result when the model's testing with the normal seismic waveform. You can see that the fitting is quite good, and the correlation coefficient value is higher than the other signals. And the figure on the right shows that their distribution. You can see that for normal data, it's basically have a higher CC value. And for the anomalous data, we are expecting have some lower CC values. So this is how we can apply it to continuous data sets. So this is the example of the 1 day, 24 hours of continuous measurements. You can see that we cut it into a 1 hour chunk. And the blue one is the model input, the red one is the model outputs, and the small text over here shows their CC value, which is the proxy of the data quality. And you can see that for some anomalous waveform, the CC value is low, and for some of the normal waveform, the CC value is high. And we can do that for a longer term. This is 8 months of continuous data for the Alaska station, the IL-15. You can see that there is a sections, the duration is about 1 month, where the CC value is significantly lower than the other time period. And if you look at the time series data, this is the 30 days of continuous time series waveform. You can see that it's actually something wrong for the sensor. So that's 8 months of time series data. And if we apply the model to even a longer term, so this is 8 years of continuous time series data for the same station IL-15, we see there's a seasonal variation not associated with the actual sensor problem. So after remove that, the bottom figure shows the residual, which is pure the data quality. And we see that there's a sensor degradation type of signals, which lasts for about 2 months and until the maintenance visits, which brings the data quality back to the original level. And this suggests that it's very possible that we can identify this in the very long term beforehand, so that we can make the maintenance plan earlier and to avoid the potential of data loss. We can also compare our model to the baselines. So the DL is our deep learning autoencoder model, And the random forest and logistic regressions, these are supervised machine learning models. So in order to train the supervised machine learning models, we need to provide some example anomalous waveforms in order to train. And this one is the traditional QC detector. It's called a Ch1 tool. And so you can see that for the performance on the station IL-15, the Alaska stations, they all have the very similar patterns. So which makes sense because these are the known types of anomalies, and the supervised machine learning model is specifically trained to learn this data. And also for the PYC, these anomalies are obvious to be detected. But in the case if we have a new stations or a new type of signals, and this is when our model outperforms the baselines model. And this is the example of the YKAR3, the Yellowknife array in Canada. And you can see that our model detects something that is completely missing by the other models. And the way that we can validate this is true is to compare the neighboring stations. So this is the, you can see that's the YKR3 is basically missing some detailed waveforms over here and there. And also this is the daily time series waveform. It's changing the amplitude response. So this is something that is unknown type of anomaly and is not built in our original training data sets. So which suggests that our model has the flexibility to learn this new type of anomaly signals. And next, to understand our model performance in a more statistical way, we can do something called confusion matrix. So this is something that we can do to classify the different cases, the true negative, the false positive, the false negative, and also the true positive. And and after that, we can calculate their accuracy. So for our model, we got a pretty good accuracy of 88%. Compared to the others, the supervised learning model has the highest accuracy because it's specifically trained with those provided examples. But it has less generalization capability to new type of signals as the slide showing earlier. And for the traditional QC approach, it still needs some tuning to for the case of the long-term anomaly detection task. So we further test the model's generalization capability using the GSN station, the Global Seismograph Network, which is a completely different seismic network with various different types of sensors. And you can see that without retraining, the model can already get an accuracy of 80%. So this suggests that the model is generalized and it can be easily applied to new sensors or some new data without significantly retraining. So which is good. And here's some example that the model can be directly applied to other IMS data. So this is the example for the Yellowknife array in Canada. You see that the model successfully detect about the 3 weeks of the anomaly. And if you look at the time series data, you see there's some the digitizer noise over here. And also this is the example of the NorthStar array, and the model successfully detects about 6 months of data anomaly until the maintenance visits. It brings this data quality back to the original level. And you can look at the time series data plots. There are some strange signals over here. And also you can look at the Warramunga array. This is in Australia. And the model successfully detects about 6 months of data anomaly. And if you look at the time series data, it's very hard to identify from the raw time series data. And the way that we know this is true is to compare it with the neighboring stations. So you can see that it's missing some signals over here and there. So which suggests that there's something wrong for this station. And it is hard to be detected if we just look at the time series data plot. So in conclusion, we propose a deep learning autoencoder model to detect anomaly in continuous time series data. And by using this, we can detect some long-term anomalies, which allowing for the more efficient development of maintenance plan. And also the performance, it's very similar to traditional approaches when the anomaly signals are explicit and well-defined. And our unsupervised model has the capability to discover anomaly cases that were not present in the training datasets. And also, this approach has the potential to be expanded to other types of sensor, for example, infrasound. So we recently published the results in SRL, and unfortunately, I won't be there for the live Q&A sessions, but always feel free to reach out to us if you have any question. So thank you very much.
Thank you very much, Junting, for a very interesting talk. Unfortunately, Junting is not online, so he will not be able to answer any questions. So we will go right away to the next and last talk of this session. And it's about a fascinating topic. There was a paper published in 1996 by Ch1 and Mark Richards about the differential rotation of the inner core compared to the core. And this is the topic of this paper, of this presentation. The title is Image Earth Inner Core Fine Scale Heterogeneity and Temporal Changes Using IMS Arrays by Guaneng Pang. Please play the video. Thank you.
Hello, everyone. Today, I'm going to talk about how we use the IMS arrays to study the Festsaal structure of the inner core, the very heart of our Earth. This is what we currently know about the inner core. I call it, it is a standard inner core model. The inner core is a solid board with a radius of like 1,200 kilometers at the center of Earth. It is composed mainly by iron and nickel alloy with a few light elements. Seismic evidence reveals that there's seismic anisotropies in seismic velocities. And more interestingly, it can be roughly divided into two hemispheres, with the eastern hemisphere having faster seismic velocity and stronger attenuation. And perhaps most famously, the inner core rotates at a different speed compared to the rest of Earth. One question you may ask is that, why study inner core at all? After all, it lies deep beneath us, in a place we will never physically reach in our life. But the inner core does matter. It is believed that the heat released during the inner core growth drives the liquid outer core convection, which in turn powered the Earth's geomagnetic field, so that the Earth can exist on Earth. And the Earth's inner core also serves as a really important reference for under-territory planets, such as the Mars. If the Mars is the inner core, and what's the Mars inner core like? Does it look like Earth? We don't know. Since we can't directly sample the inner core, seismic waves are our powerful tool to imaging the inner core structure. Two types of seismic waves are used. The pk-IKP, which are the seismic waves reflected on the inner core boundary. And another one is the pk-PDF or pk-big-IKP. It is the seismic wave passed through the inner core itself. One seismic wave encounters small-scale variations in velocity and density. They scatter around. These scattered energies arrive at seismometers either before the direct arrivals or more often after the direct arrival. forming a long chain of the seismograms. We call it coda. It turns out the inner core is far away from the homogeneous. If we zoom in at scales of just 1 to 10 km, velocity variations exist. These variations will create scattered wave fields that arrive later than the critical pk-IKP refractions, producing what we call pk-IKP coda. The figure here shows an example waveform recalled at ILA. You can see that the amplitude of these pk-IKP coda is extremely small. They are only on nanometer scale, which makes them really difficult to be detected with only a single seismometer. That's why we need to use the small aperture seismic arrays to improve the signal-to-noise ratio. The figure on the right here shows array geometries for each array used in these studies, with the IMS arrays highlighted in blue. Previous studies were restricted to small regions. But the global deployment of the IMS array provide a really excellent opportunity to build a global pk-IKP dataset. Then we can map out the global inner core 5-scale structure as the map shown here. As the map shown here, the IMS dataset gives us broad global coverage, including a lot of regions that have never been studied before. Panel A on the right figure here shows an example pk-IKP coda observations from the region E8. The coda has a spindle-like shape. The energy grows gradually, peaks, and then decays. This shape reflects the inner core heterogeneous structure. By measuring the growth, decay, and the total duration of these coda, we test whether hemispherical patterns like those we have seen in attenuation and entropy exist in the inner core 5-scale structure. The answer is no. Instead, we see strong regional variations, but there is no systematic hemispherical difference. By modeling the pk-IKP coda, we can estimate the seismic scattering strength in the inner core. The figures here show the global 3D inner core heterogeneity structure we obtained from the IMS array observations. The maps on the left show map views at different depths, and the figure on the right here shows a depth profile view from the North Pole. Darker regions indicate stronger scattering and greater heterogeneity. There are some key points we need to notice. The first one is that you can see the scattering is presented everywhere. It has strong regional variations, and the most importantly, the scattering strength increases with depth, which means the deeper inner core is more heterogeneous. This depth dependence tells us something about the inner core growth. The stronger scattering at depth cannot be explained by the classical inner core growth model, which states that the inner core has gradually grown today. Instead, it's just a phase of rapid growth early in the inner core history, likely tied to the delay in nucleation caused by the superquake. The core did not crystallize intermediately at the solidus, but supercooled until it overcame the nucleation barrier. Then it grew rapidly to hundreds of kilometers in thickness within thousands of years. After that, it gradually grew until today, but some liquid will trap inside the inner core and then gradually freezing. By comparing our scattering results with porosity models, we infer that the inner core nucleation was delayed by about 0.07 to 0.12 inner core age, involving supercooling of 20 to 30 K. Here, the inner core age was calculated from the moment when the core temperature dropped down to the solidus. The inner core differential rotation, it is one of its most debated properties. This idea was proposed over 30 years ago, but then debates continues. Indeed, there's observations that there's change in the inner core seismic waveforms, but people has been arguing about like these changes are caused by non-rotational changes like the inner core boundary change, not the inner core superrotation. Here, using the PKB-IKB coda, we analyze the earthquake doublets. An earthquake doublet is a pair of nearly identical earthquakes separate in times. There are PKB-IKP waveforms, so intermittent changes. The figure here shows examples from Isla. Clearly, only the earthquake doublet in between 2002 to 2009 saw changes in PKB-IKP waveforms, not that doublet from 2004 to 2017. When looking globally, the picture becomes more clear. Each line in the right-hand plot represents a doublet, with the red indicate PKB-IKP change, and the blue indicate like the no change in PKB IKP coda. Panel A shows the polar rate path, and panel B shows the equatorial ones. All in doublets spanning the time 2001 to 2003 display changes in PKB-IKP coda, and the polar seismic rate path shows largest effect. This is expected from the differential rotation, since the polar rate paths are most sensitive to the change in inner core relative to the Earth's west to east rotation. So this suggests that the inner core experienced a burst of differential rotation during 2001 to 2003. Before and after that, the differential rotation was small, tiny. But what happened after 2003? We expand our dataset to 2023 and focus only on polar rate paths. We find that the PKB-IKP coda from 2002 to 2009 saw changes as shown in the black and red waveforms in this figure. But then by 2022, the waveforms match again as shown in the blue and black here again. This indicates that the inner core rotates back to the same position. By investigating the time spanning from those earthquakes doubling showing no PKB-IKB changes, we found that the inner core superrotated from 2003 to 2008, and then subrotated 2 to 3 times lower back to the previous position. Even more, we find evidence for non-rotational changes. As the waveforms shown here on the left, some doublets after 2004 saw waveform change, tiny waveform changes in array YKA, but not on ILA. According to the rotation model we proposed, and these waveforms should follow the red star on this figure here and should not have changes on PKB-IKP waveforms. Yet, tiny waveforms changes occur on only YKA. The seismic rate path to YKA samples shallower than the seismic rate path to ILA. This suggests that only the shallow inner core has structure changes. Perhaps the whole shape of the inner core is distortion. These are discoveries we have made about the inner core using the IMS arrays. All works have been published. Please go through our papers if you are interested in details. Thank you very much.
Thank you very much, Guaning, for telling us about this fascinating topic. So one question that we have is, what is the relationship between this differential rotation of the inner core and the geomagnetic field? Can you expand a little bit on that?
Yeah, I mean, the answer will be like, I think there's still a lot of unknown of the detailed relationships, because like, for sure, people now believe that it's the inner core drives the outer convections, but mostly it's from the heat, from its cooling. But for sure, one like the inner core is differential rotated, or even it has some like, or it's straight changing, so it may in some way
to change the pattern and optical conversion that will ultimately affect our geometric field. For sure, it needs more jobs and more combining the geometric observations, and even more high performance modeling, and then a more detailed models of inner core decadal changes to help us answer these questions more clearly or like more detailed. Yeah.
So is it envisionable to have a very complex model that would at the same time model the rotation and the geodynamo?
Well, I mean, I can see that there's some possibility there. If we can at least from our seismic side, we need to provide an accurate model first, right? I mean, we need to have an accurate differential model first. Then the people like geometric field people can use it in their simulations. So yeah, I can see there's some potential here, but also there's a lot of effort we need to do like in this topic too. I mean, especially like the resolutions and timing here. Yeah.
Okay, thank you very much. Again, fascinating topic.
Yeah, thank you.
Thank you very much, Wan-Ning, and thank you very much to these 7 authors for outstanding presentations. We believe that it has been a great start of the scientific sessions of Science and Technology. And now we are going to move to the poster sessions. If you are interested in posters related to waveform technologies, please stay in this channel, channel 1. There will be poster presentations about seismics, hydroacoustic, and infrasound contributions. If you are interested in other topics, for example, radionuclide, on-site inspection, global challenges, outreach, and others, please move to channel 2. You will see on the left side of your screen that you can choose between channels 1, 2, 3, and 4. So I repeat, we will now take a short break of 5 minutes. If you are interested in waveform technologies, stay in channel 1. If you would like to listen contributions about other technologies, move to channel 2. See you in 5 minutes. Thanks a lot for watching, and let's have a great Science and Technology 2025 conference.